Hey, John here. Let's take a quick review of what a heart is and how it connects to memory and what it does, right? A heart is essentially the part of a processor that does all the execution of the instructions, right? It fetches them out of memory, it does the operations that are required, stores the results back into memory. Heart contains the register file, the ALU, finite state machine, all the stuff to make it go, right? It can have a cache, it can have an MMU if it supports virtual memory, and it might have some other features as well. But what it entails is everything that is needed to execute a thread, okay? That which is needed this is basically a thread. My handwriting isn't functioning this morning, right? Thread of execution. That's really what this thing means. A hardware thread. Now, let's say you taxed out your ability to run this machine as fast as it can go, and the nature of your program is such that it could run more than one thread at the same time. Well, in that case, you could add another heart over here. In fact, you could add many, right? Dot, dot, dot. And you can just hook them all up to the same memory like this. ALU, cache, and the MMU, right? And these can just keep on going. So what happens when you have more than one heart in a system at the same time? Well, starting it up is a little bit different, as you might imagine. You know, how do you give one heart something to do and another heart something else to do? Or maybe they're both collaborating on the same program at the same time by dealing with data in different sections, right? So a very common way to handle this is to give each one of them an ID number, like 0, 1, 2, and so on. And then you provide a way for the code that's executing on one heart or another heart to ask, you know, what's my ID? How do I get this? Okay. And then it can execute code based on its ID. This is essentially one way you can use to start this kind of a system up. You can essentially have a switch statement in the simplest of terms that says, you know, if my ID is 0, have a case, execute, you know, main 0. And this one might come along and says, my case 1, execute main 1. And this one might have another case for that one called, you know, case for main 2. And it might look something like this. Right? So you might have int ID equals something, right? We'll talk about that in a minute. And then you might say case 0. And you say main 0, right? Break. Case 1, main 1. Get my semicolon. Break. And so on, right? So that way, if each one of these starts executing the same code, and we'll see that's how this thing is going to start up. When we reset each one of these hearts, they're going to all be exactly in the same state. And that is their program counters will all equal 0. So what does that mean, right? So essentially you have to execute logic that looks like this. You have to say, give me my ID, and then ask, you know, if my ID is 0, do one thing. If my ID is 1, do something else, and so on. So let's look and see how this might be done on a simple RISC-V system. So let's start by looking at the differences between the simulator that runs with only one heart and one that has multiple hearts, all right? First thing you'll notice is I added one new command line configurable option called number of hearts with a default of 1. So by default, this will run the same single heart type of operation as our regular simulator does. And we have the H case in here to handle it. And read in an integer value and just simply store it in the num hearts value so I can override that default. Now, the only other difference down here is when I create the heart object. I'm going to create one that has only one heart or multiple hearts. The constructor is a little bit different. So if you have only one heart, all you need to do is send it a reference to the memory object so that it can fetch its instructions and its operands and store its results and so on, right? Now, in a multiple heart system, we have to tell the CPU object that we're going to create how many hearts it's supposed to have, and as well give it the memory reference, okay? The rest of it is the same. When we call reset, what we're really doing is resetting all the hearts if it's got multiple hearts, or the one and only one in this case here, right? If we say show instructions or show registers, or even if we say run, these things all apply to every single heart, not just the one heart that you would have in this case here, okay? And then if we dump out the state of the CPU, and we have multiple hearts, what we're doing is dumping out the state of every one of the hearts. Okay? The memory system doesn't know nor care how many hearts it has. So when it comes to dumping out memory, there's no change at all. So let's look and see what this multiple heart class looks like in contrast to the single heart class for this particular simulator. So, multiple heart, what does it do? Here's the constructor, number of hearts, memory reference, and it has the usual accessors and mutators to reset, run a program, and dump out the state of the processor. Now down here, notice I have a vector of single heart objects. Well, that makes sense. I have multiple of them, right? Now this literally means that I create an entire single heart object for each one of the hearts that is being represented by this multiple heart class. So there's nothing special about one versus another. Okay? Absolutely nothing special. If we look at the source code of the methods of this class now, what we're going to see is every one of these pretty much just simply says, hey, well, let's start here and I'll come back to the constructor in a minute. If I call set show instructions on my multi-heart, all I'm going to do is just say for every heart in the vector of hearts, propagate that setting to each one of them individually. If I want to show the registers, propagate it in, okay? And so on. If I want to reset it, reset all of them. If I'm going to dump them all, right? That's pretty straightforward. Now, if I'm going to run my multi-heart CPU, this is essentially the same thing as just passing it on to all the other ones independently. But it's not as trivial because what we need to do is have each one of the hearts execute one single instruction at a time in unison. We can't just let one of them run until it's done and then fire up another one and so on, which would be much more akin to if we did it like this, okay? So we have to do it in phases here, right? So what do? The first thing we're going to do is initialize all the hearts. And what that does is it will set x2 equal to the memory size like we did in the single heart class. We'll have a look at that in a minute, okay? So what's happening here is we're going to tick each heart once and only once every time we go around this loop. So what we're really doing is we're going to tick all the hearts, then we're going to go around and tick them all again and tick them all again and so on. We're even going to tick the ones that are halted, by the way, as a side note. But the tick logic inside each one of the hearts, the first thing it does is ask, am I halted? And if I'm halted, I don't do anything kind of logic, all right? We're going to take a quick look at some of that in a minute. Now, when it's done and all of them have become halted, we then execute the run fini, okay, which is the thing that prints out my termination status and the instruction count for each one of the hearts. What do we do when we construct our multiple heart processor? Well, the first thing we do is this. Now recall that hearts is the name of our variable that is the vector of the single heart CPUs, all right? Now, if you're not intimately familiar with how C++ vectors work, let's look at this really quick. This is an initializer list, right? So it says when you construct this multiple heart object instance, construct its member variables using these arguments over here. And when you construct a vector object, what you can do as one of many options, you can say, put this many elements in the vector, and when you construct them, pass each one of them this argument for its constructor. And that's exactly what we need. Each one of the single heart CPUs, as you recall, needs the memory reference in order to be constructed. So this is how we construct a plurality of heart objects, okay? Then we go into a loop down here and we say, well, for each one that we just constructed in our vector, because this takes place before the body of this constructor starts running, we're going to go through there and we're going to call this setMHeartID function. And we're going to give it a number. This is where the heart ID numbers are going to come from that we just saw in the diagram, okay? And what we're going to do, I'll show you in a minute. We'll look at the single heart object implementation, and what it's going to do is it's going to create a header string. The whole point of this is two pieces. Number one, make sure that each heart has its own known unique ID number. And two, because this is a simulator and it generates debugging output, we need to know which heart generated any particular debugging line that it prints. So what we're going to do is we're going to see this is going to create a header, all right? So this is the entire multi-heart CPU implementation that just creates a bunch of single hearts. Now let's look back at what the single heart looks like, okay? So here's the constructor with its single argument, right? And we pass that to its base class, which is the heart for the RV32i class, okay? You'll notice I added an init and a fini here. I also added these down here. Okay, look what happens if I call tick on this single heart class, which is different than what happens when you call tick on the base class in the RV32 heart object, okay? So if I call tick on a single heart object, what it's going to do is it's going to go up and say, all right, I'm going to just reach over and call the tick function in the base class, and I'm going to pass it this header string, which is sitting down here, okay? He's going to do the same thing with the dump. All that's going to do is allow you to call the tick and the dump functions in the base class down here and pass it in a header string, which, as we'll see, is going to be filled in with the heart number so we can see what's going on in our debug output. And that gets created in this function right here, okay? So if you call the setMHeartID on the single heart class, pass it a number, what we'll see it will do is we're going to put a string in here with that heart ID number in it, okay? So let's go ahead and look at the changes in my single heart class. See how this works. It's all straightforward, okay? Here's my run method. Now, you may have put this reg set mem get size line of code right in here. That's fine. I factored it out. Why? Because if we want to run with multiple hearts, we need to initialize each one of the hearts independently of all the other ones. In other words, we're not actually going to use this run method in a multi-heart CPU. Okay? This is only useful in a single heart CPU. And what it needs to do is set x2 equal to the memory size before it enters its main loop that ticks all of its instructions until the one core becomes halted. When it's done, it is going to print out some statistics. It's going to say why it halted, how many instructions have been executed, and whatever else it might do. Okay? So I just simply factored out the initialization in the fini code from my regular old run loop. I mean, should have probably done that in the first place, right? This is the other thing that's been added. Okay? What does this do? Well, if I set the heart ID in the single heart object, it's going to reach up and send it in its base class, right? Because this is going to override the same function in the base class, right? So we need to make sure the base class knows its heart ID so that it can execute a CSRRS instruction when we want to ask, what is my heart ID? And we're going to see that's how this happens, right? So what else does it do? It's going to create a string. It's going to open square bracket. It's going to have the heart ID number in there, a close square bracket, and a single space after that. And it's going to save it in the header variable. So after this, it should be obvious what really happens as a result of this, right? All it's really going to do is put the heart ID numbers in each one of the hearts, create that prefix string. Then down here, when I say, look, I want to initialize all the hearts, it literally is going to just simply set the x2 for each individual heart. Okay, remember, they all have their own register files. So every one of those needs to be independently initialized, okay? And then when I run my main loop over here, when I call tick, remember, I overrode tick in the single heart class, and it will pass on the call to the one in the base class along with its header. So now every time I do a tick and I execute one instruction, if the debugging flags are set, and each individual heart prints out its registers or something like that, it'll be prefixed with the heart number in square brackets so we can see what's going on, right? And then when it's all done, it'll also print out the statistics with the same header information included as well. Now, there's one more thing that I did. Made a minor adjustment in my regular base class for the heart, okay? What I did in here is I added one little if in here. Probably should have put this in there to begin with. As you can see, as I mentioned earlier, if this individual heart has become halted, this flag would be true, and it does literally nothing and gets out right away. If it's not halted, it counts the number of instructions that it has executed. It'll dump out the registers if it's been asked, and so on. This is the important little bit that I just added. Why? Because I accidentally wrote a bad program, and this is another reason that the heart should halt itself. Look what's happening here. If I have a program counter that is ever loaded with a value that is not a multiple of 4, then this expression will become true. And that is completely illegal in an RV32i processor, okay? It's not illegal if it has the C extension, right? If it was an IC for compressed instructions. That's why they allow it in the design of the processor, but it is disallowed if you do not have compressed instructions. So in this simulator, which does not have compressed instructions, we have to shut it down and halt it if the program counter ever has any value that's not a multiple of 4. I will set the halt flag to true, and I will remember why I halted it. So when it's time to print the status of the machine and why it halted, it has a little message that it can add in its output. How then do we write a program that can run on such a thing? Let's start with the basics. So after being reset, each of the individual hearts will start executing code at address 0 in memory. And if this is what's sitting in address memory, every single one of the hearts will put this address of this symbol into their respective GP register in their own individual register files. So they'll all end up setting it to the same value, which ultimately makes sense because they're all executing in the same address space, okay? So what the heck is this all about? Well, if you go grab the privileged instruction manual for RISC-V, it'll tell you what these instructions do. It's a rather lengthy manual, but the short of it is CSR stands for Control and Status Register. And what we're going to do is read Control Status Register number F14. And we're going to put its value into X5. Well, in short, this whole thing means nothing more than tell me the heart ID that is executing this instruction right now and put that number into register X5. So what's going to happen is if we're running on, say, 2 different hearts, one of the hearts might get one number in the X5. The other heart is going to get a different number in register X5. So this is how the code's going to figure out which heart it's running on, okay? Now, because we have one single address space, think about this for a minute. If we're going to call any subroutines, well, each heart needs its own stack, okay? So we know the other thing that happens on this particular simulator is that the stack is set to the number of bytes in the memory. So we can use it as it is if we have only one heart as our stack pointer. If we have more than one heart, what we need to do is make sure that each of those stack pointers point to a different place. So here's what we're going to do. I'm going to take the heart number and I'm going to multiply it by doing this. I'm going to multiply it by hexadecimal 100 so that each heart can have a different value for its stack pointer. Otherwise, this won't work correctly. Okay? You cannot have more than one thread of execution using the same stack memory, right? They're going to clobber, it'll get all corrupted in there. Okay? They have to have their own. So, let's review how this thing works. I'm going to shift the value in X5 left 8 bits. I'm effectively adding 8 zeros onto the right side of that value in binary, which is adding 2 zeros in hex. So this, just like we learned in first grade, right? Oh, how do you multiply by 10? Well, you add a 0. How do you divide by 10? You remove a 0, right? We're shifting left and right. We've known how to do this our whole lives. Perhaps we were taught wrong, but that's what's really going on there, right? So if I'm shifting left a value, I'm multiplying it by powers of 2, okay? So I'm multiplying this by hex 100, which is 256 in decimal. So what this is going to do is it's going to say if the heart number is 0, so then I will just be calculating the value 0 in that for heart number 0. Now look what I'm doing here. I'm going to subtract from x2 and then store the result back in x2, right? Remember that x2 is our stack pointer, okay? So heart number 0, what am I going to do? I'm going to subtract 0 from x2 and store the result in x2. I'm going to leave it untouched. But if the heart is 1, what's going to happen is 1 times hex 100 is 100 in hex, right? So then when heart 1 comes out of this subtract statement, its stack pointer will be 100 in hex less than the stack pointer that's in use on heart number 0. Okay, so let's make sure this all works and we all understand what's going on before we try and move any further. So I have a nice rule in here called make run. Let's look at our make file really quick. What it's going to do is it's going to run my simulator. I'm going to say I want 4 hearts. When it runs, I want to see all the instructions. I want to see all the registers. Before each instruction executes, it'll dump all those. When the entire thing is done and all the threads, all the hearts have been halted, I want to dump out all the memory in the state of all of the hearts, okay? And the memory size for this is going to be 800. So if I say make run, this will run my whole program. There's the memory dump at the end, and I'm scrolling back in here. Here's the code running from the beginning up here. Now, we've run it with 4 hearts, right? Here's the little header string with the heart number in it. So this says, here's what heart 0 is doing right now. It just executed an OEPC, and it accomplished setting x3 equal to this value over here, which is 2,000. Okay. Now, the heart number 1 does the exact same thing because it's still executing its first instruction, right? Heart number 2 does the exact same thing. Heart number 3 does the exact same thing. No problem, right? So there's the OEPC. And we've seen this before. Load address ends up turning into 2 instructions. It's an OEPC and an add immediate. Okay, so there's heart 0 executing its second instruction. Heart number 1 executing its second instruction. Heart number 2, heart number 3, and they all end up calculating the value that is supposed to be put into the GP register, which is this number here, 1818, and stores it in X3, okay? After that, what does it do? Well, here is heart 0 executing the CSRS function that we just saw in there, which has the effect of storing 0 into X5, as you can see here. When heart number 1 does that same instruction, it puts a 1 into X5. Keep in mind that every heart has its own registers, okay? So before this is executed, here are the values of the registers in heart number 1, okay? Register 0, 1, 2, 3, 4, 5, and so on, right? So before heart number 1 executes its CSRS, it's got basically garbage in register X5, okay? As do all of them. Here's heart number, 2 down here, and it gets a 2 in X5, and heart 3 gets a 3 in X5, and so on. Now we go back to Hart 0. Look what's going on down here. Here's what's going to start shifting left and all that. So when Hart 0 did its CSRS function, and we now can see the registers after that has completed. Okay, look what's in register X5 right now on Hart 0 before Hart 0 does this operation. It's got a 0. Well, what does Hart 1 have in register 5 before it shifts it to the left? It has a 1. Those are the Hart numbers, okay? So we can see that that clearly worked. Here's the 2, and here's the 3 for all the other ones, all right? Now, when Hart 0 decides to subtract its register 5 from its stack pointer, it's subtracting 0 from the 800 in hex, right? When Hart number 1 subtracts its version of X5 from register X2, it's subtracting 100 in hex, okay? So the next time we see the registers for Hart number 1, this 800 should change into a 700 in hex, okay? And likewise, as we go to the other Harts, right? Hart number 2 is a 200 over here. Hart number 3 has a 300 over here. So we can start to see that the state of each one of the individual Harts has now diverged from each other. All right? And as you saw, right after we do all that, then each one of the Harts would execute the e-break function. So as we can see, the registers at the time that Hart number 0 executes the e-break, its stack is still set to 800 in hex. When Hart number 1 executes its e-break, its stack is at 700. When Hart number 2 stops, it's at a 600, and so on. Okay? Hart number 3, its stack starts at 500. All right, now here's the termination. All of the Harts have halted. So we run the Feeney code, and each one of them have executed 6 instructions. That makes perfect sense, because we have not yet done anything at all to cause any Harts to do any different instructions. They all ran the exact same programs. They got different results because they have different data, okay? Here are all the registers after the all of the Harts have halted, which is, we've just looked at it. It's the same thing, 800, 700, 600, and 500 in hex for the respective stack pointers when they start running. And we can still see over here that the core number, the Hart ID number, times 100 in hex is still sitting in that register there. And we can see the memory down here. Not that none of it's really been used, so that doesn't really matter, okay? What's the takeaway here? The takeaway is that this code can be used to let each Hart run its own thread of execution and to differentiate what it's going to do from the other Harts. And it's all keyed on its Hart ID. So at this point, what do we know? We have what? We have 4 Harts. And one of the Harts was set up so that this is our memory, right? And if the address 0 is down here, and what do? We in that particular run, we had 800 in hex bytes, right? One of the Harts stack pointer is left up here. We'll call that one 0 SP for Hart number 0 stack pointer, right? Another one is down here. That's for Hart number 1, and it'll be initialized as 700 in hex. This one here is at 600. 3 SP is down here at 500 in hex. It's the only difference between the states in each of these 4 Harts at that point in the code. Now, since each one of them has its own separate region of memory, if they all were to call some subroutine, what would happen is the subroutine stack, if it created local variables and stored its registers on Hart number 0 would be stored up here. Hart number 1 would use this for storage here. Hart number 2 and so on would have all their own separate storage areas. This is the entire purpose of getting all these separate stacks set up like this. Now what do we do? Well, remember we got the text, we have the data, we have the BSS, heap in here. It grows up this way, and now we have multiple stacks, okay? somebody still has to zero this thing out before we actually call any real subroutines or use this in any way that we would recognize, okay? So we have to zero out this BSS. So we have to kind of decide which hart is going to do that job and what do the other ones do? Can the other ones go off and do other things? Well, not really. They all have to wait until the BSS is zeroed out, because if it executes any regular code in here, like from a C compiler, it expects the BSS to have been zeroed out. Such code will also expect the library to be initialized, okay? So something has to zero out the BSS, and it has to initialize the library, or libraries, okay? This has to be done, right? Now, if you think about it, if each one of the harts just simply stored a bunch of zeros in here, that wouldn't be the worst thing. They'd all be doing the exact same thing. They would set memory address, whatever. Let's say this is at, say, 100 in hex or something like that. It would put a 0 there, and as well as all the other harts. There'd still be a 0 there when all the, when the smoke rises, when all is said and done. Okay? So we can let them all do that. Okay, but what if this was enormous, like a gigabyte? Now, how long would that take? Now, you might argue that it would take the same amount of time if you did it with all the threads versus only one thread. Well, that's not really true. Okay, because remember, if I let this hart write a bunch of stuff into the memory, at the same time this one here is writing stuff in the memory, only one at a time can actually do that. Okay, so it will literally double the amount of time it takes to clear out this BSS if every single hart is trying to write to the same memory byte at the same time. They'll all go one after another. So it would be nice if only one of the harts cleared out the BSS while all the other harts waited somehow. We also have this problem that we have to initialize the libraries. So that raises the question, is this what we call reentrant? The answer is probably no. If you don't know that a function is reentrant, then you must assume it is not. What the heck is reentrant? All right? A reentrant function is something that can be executed at the same time by more than one thread. For example, the CRT code that we're just looking at is reentrant. Okay? Because it has to be. All the threads, all the harts at the same time are able to execute the same code without getting in each other's way. Okay? But as soon as we get to the point where we're zeroing out the BSS and we want to initialize the libraries, that's not true anymore. So we need to find a way where we can get one and only one hart to do this job while the other harts wait. And when this job is done, then all the harts can continue on their merry way and do whatever comes next. So how the heck are we going to do that, right? Well, let's go back here. Think about this for a second. In this particular design, there's no way for a hart to communicate with another hart directly. It's not like it can stop and start them back up again. There may be CPUs out there where they can work that way. I mean, this is why different companies make different CPUs, right? In the simulator that we're using, we don't have any way to make that happen, okay? So what is shared between all these harts? The memory is shared between all these harts. So if we know that we're careful and we do a very specific order of operations, we can set some flags in this memory so that each one of these harts can figure out what the other one's doing. All right? And that's really useful, especially if you want to stop a bunch of harts and then resume them later. So how are we going to go about doing this, right? All right, let's say there's a flag in memory somewhere. Let's say this byte right here. I'll just put a circle right there, whatever address that is, okay? Let's call this one the init done flag. All right? What are we going to do here? If we can know that the done flag is false, right? So if we can set it to 0 early on in the initialization code, then what we can do is we can take the a heart number 0, thread 0 up here, can call the initialization routine, 0 out the BSS, whatever it wants to do. Okay? When it's done, it can change this flag to a 1. So let's call this init done. Right? So we set this to false. And we have to make sure it's set to false before any of these hearts reads it. Because, when you first turn on a machine, the memory could be full of garbage. And by definition, it definitely will be full of garbage. It may or may not be 0. So we need to make sure this flag is 0 before any of the hearts read it to ask, is that flag set to 0 or a non-zero value? And if it's non-zero, presumably, that means that thread 0 up here will have completed its initialization logic, okay? So what do we do to make that happen? Well, like I said, it actually is okay if every single heart does 0 out the BSS. It'll just slow the process down. It'll become agonizingly slow if the BSS is really big, okay? But what if one single byte in the BSS, we don't care. Well, 1 byte, it's okay. So if all the hearts 0 out this done flag at the same time, there'll be some contention setting this one to 0 here. That's okay. Just don't do the whole thing. Once this flag is set to 0, heart number 0 will proceed to do all these operations here. And any hearts that have a non-zero ID number will continuously read this flag, waiting for it to become a non-zero value. When it becomes non-zero, they will assume that all the initialization code up here has completed. So let's look at that version of the code. All right? So what we're going to do, all the hearts set the global pointer. Here's all the hearts putting a 0 into the init done flag, the 1 byte. The init done is going to be defined down here, right? Remember LCOM, this allows us to put 1 byte into the BSS and put a label on it called init_done, all right? So what this code up here is going to do is put the address of that 1 byte into X5. Then we're going to store a byte into that address. We're going to put a 0, because X0 is always 0, into memory at the address that's stored in X5 right here. Then we're going to do our call to CSRS, find out what heart we're on. We're going to set up our stack. And then down here, we're going to ask, look, are we heart number 0, right? If X5 is not equal to 0, go to wait on heart 0. Remember, if X5 is 0 up here, even if you multiply it by 100, it's still 0 when we're down here, okay? So if it's not 0, we know we're not heart 0. So it's going to branch down to the label down here. And this is where this loop is, okay? So what's it going to do? It's going to say, all right, put the address of init done into X5. That might be redundant, but that's okay. And then we're going to go into this loop here. We're going to say, go ahead and read the value 0 off of X5 and put it in X6. And then say, look, if X6 is still 0, go back up here and keep waiting. It's going to spin very quickly in here. And it'll stay in there until something somewhere changes the value of the init done flag. This is how we're going to cause all the other hearts to wait, to keep things synchronized. All right? Now, what does heart 0 do? Well, it knows that the contents of X5, which is 0, is equal to X0. When it executes this branch not equal function, it will proceed down here and do all of this. And what is it going to do? It's going to go ahead and 0 out the BSS, right? We've looked at this before. I might slightly optimize this loop. This is a very common thing you're going to see. I thought I'd throw this in there. Take advantage of this moment to digress into this little tangent here. What you normally see in a loop like this is you don't have a condition here that says finish it and go down here, and then you do the operation and go back up and check every time at the top of the loop. Okay? What we do is we optimize away the common case of the loop iterations, all right? So what we really do is we're going to ask, are we done before we start? In other words, is there nothing to do? If and only if there's absolutely nothing to do, just skip it and go down here. Okay, if the BSS has no bytes in it. That's what Hart 0 will do. And it'll proceed down here, and we'll see, set the flag to 1. But if there is something to clear out in the BSS, we don't need to put 4 instructions in this loop, and we can do it in 3. That's a 25% performance improvement right there, okay? What are we going to do? We're going to store a 0 byte. We're going to add 1 to the address pointer, and then we're going to ask, does the address pointer reach the end? And then we're going to say, if rather than just unconditionally branching around to up to this instruction here, we're going to do the same condition backwards down here. Say, if we're not done yet, go back up here and keep going. Okay? There's a slight difference in how this thing is written for a 25% gain. Now, arguably, we could get another 25% gain by storing full words into memory instead of individual bytes, right? And of course, if we did that, that would be a 16 times total gain, right? So this is not the most efficient code, all right? But, you know, these types of things are what you got to keep in mind. Now, why did I do it in bytes instead of in words? Well, I could have used words if and only if I can know for absolute certainty that BSS start and BSS end are always a multiple of 4. It turns out that will be the case, okay? But in theory, I can't be 100% certain. And I didn't want to cloud and muddy the waters any further, okay? So this is just going to zero out the BSS in what I would argue is the otherwise normal way that we've done it before. When Hart 0 and only Hart 0 is done with that, it falls down to here and it puts the address of init done into X5. It puts a 1 into X6 and then stores that 1 into the flag. Now Hart 0 will stop here, of course. And all the other hearts will also stop down here when they're done spinning down here. All right, so this is one step further than where we were before. So now we have the code that will initialize all our stacks. It'll zero out the BSS, and it will synchronize things so that all the hearts proceed forth, which in this case it'll just simply stop, at the point in which everything is ready to go. So before we do anything else, let's make sure this works, okay? The make file for this one, what do we got? It's going to run our simulator on, we got 2 hearts this time, dumping out the pre-trace register and instruction information. For every instruction it executes, the dump at the end of the program, we're going to have 2,000 and hex bytes. That's 8K, we say, in decimal, all right? So let's go ahead and make this file. Then we're going to run it. We got a lot of output. Let's pipe that into less. We don't need to walk through every single thing. The bottom line is we have our 2 cores, and we can see them both doing the OEPC and the add immediate to load their GP registers, right? Then what does it do? It's going to do the OEPC add immediate again, and it's going to, each one of them are going to store a 0 into the done, the init done flag. That's what's happening here. Both cores do that, okay? That's okay. Then we're going to go grab our core ID for Hart 0, the Hart ID for 0, the Hart ID for 1. You can see they change. And the usual thing, multiply it by 100 in hex, do the usual stuff, go on our merry way. Eventually, there's the subtraction for the stack. And then on Hart 0, it's going to ask, does X5 equal 0? And the answer in this case is yes. So it's going to go to hex 24. It's going to branch to 24. And the other heart number 1, is going to ask the same question, but its X5 has 100 in it and not a 0. So it's going to end up at 58. So it's going to jump over the init code in, you know, in the obvious way. And here we're going to wander through the code and see that the BSS would be getting zeroed out in Hart 0, while Hart 1 is constantly saying, give me the byte, and asking, is it 0, is it 0, is it 0? And Hart number 0 is going to be storing zeros into the BSS, okay? And it'll go round and round and round until they both end up becoming satisfied with whatever the stopping condition is, right? Which is, in the case of Hart 0, it has finished zeroing it all out, and in the case of Hart 1, it is when the flag changes. So here is Hart 0 stopping, okay? And the last thing that heart 0 did is up here. It's this instruction right here. You can tell because there's zeros, right? In the left, the heart ID is over there. There's the store byte of the value inside X6 into the memory, whose address is in X5. And you can see in the debug output here what that is 106C plus 0, right? 0 is this offset here, the immediate operand. And it's setting it equal to the value of 1. You can see the little 1 hiding over there. It doesn't quite fit on my screen, okay? So this sets it to 1. And the next thing heart 0 does is it does an e-break. And while that's going on, heart number 1 is still loading. Is it done? Is it done? You know, is it set to 1? Is it set to 1? Well, in this case here it is. And we could scroll up and find all the other times it checked. But eventually it's going to get to the point where after heart 0 stores a 1 in there, it's going to load it and put it in X6. And we can see here at this time it got a 1, right? So heart number 1 now, when it says, hey, is the contents of X6 equal to 0? If it is, go to address 60 and loop again. But in this case, it's not. So instead, it'll go to address 68, which is the next instruction to execute after this one. It falls through, right? Because the condition's false. And then heart number 1, as you can see here, is halted. And at the end of the run, we see that both hearts terminated from an e-break instruction. In this case, heart 1 did one instruction more than heart 0, which is not too surprising because heart 0, remember, sets the flag and halts right away. While heart 1 has to see that by reading it and then do a branch to find out, you know, whether or not it was set to 0, and then it halts. So it does make sense that we'd see at least one extra instruction executed in heart number 1, and here's the status at the end of everything. Heart 0 has a stack that's in a different place than heart 1. That's a very good thing. Okay. Now let's do an NM on this program. Let's go ahead and sort the addresses. Right? Because here's my init done flag. It's at 106C, right? Let's go ahead and run it again and go down and look in the memory at 106C. Got to back up a little bit. Oh, we saw some data. There it is right there. Here's 106.0. 106C is right there. So it turns out the only thing in the BSS are these 4 bytes. Okay? And by the time it got done initializing in heart 0, stored a 1 in there, there's that 1. We can see it sitting right there. So now we know we can set things up. Now what if we want to call a C program, right? What changes do we have to make in there, right? Well, the only real change is we got to remember to call the init array. And because init array may or may not be capable of running more than one time, we need to make sure we call it once and only once, right? So what I'm going to do is I'm going to just stick a call in here. The only difference so far is call libc init array in the code that's executed only by heart number 0. And do so before you set the init done flag. So none of the other hearts go on and start using things and calling routines and stuff like that, right? We need to know that the entire BSS has been zeroed out, as well as any libraries that we're going to call have been initialized before anything happens, okay? So heart 0 is going to be charged with that. It's going to set the flag, and then heart 0 is going to call main and then stop. All the other hearts wait for heart 0 to finish all the initialization. And they're also going to call main and then stop. So the only differences are that we added the initialization call here, call main in heart 0, and then we added a call main for all the other hearts as well. So what does this boil down to? It says that all the hearts, once they become synchronized, are going to call the same function in main. What does main do? Let's look at this. What main is going to do is it has this array here. And what it's going to do is it's going to execute this instruction. I'll talk a little bit about this in a minute. The short of it is, this is how you can just say, look, in the middle of my C program, put this assembly language, one instruction in here. There's no way to express this in C, so just do this, please, okay? And what we'll see is that this essentially puts the heart ID number into this variable, okay? Once that's been done, I can say, hey, here's an array of flags, and I can set each one of them, if I want to my heart ID. We'll also make sure that this is all working fine by returning the value of the heart ID when main ends and goes back into CRT0, which we know it'll do an e-break immediately after this return. Okay? Now, this is going to let me easily check to see if this worked okay. And I say easily because I know that if I return my heart ID in main and it goes back into CRT0 and it does an e-break right away, I can immediately go to the post execution dump in the debug output and check and see what's in register X10, because that is where the return values go for functions. Okay? So I can go to every heart and look and see what's in X10 and make sure that's the heart ID. All right? So that's the only reason I did this. Make it easy to check. And we can look at it in a second. Now, let's look at how this thing works. Now, I try to avoid this as much as possible, but there are times where you just need to be able to do it. This is a directive to the GNU compiler. This is not portable by any means, okay? What you're going to do is say, look, I want you to emit one assembly language instruction right in the middle of the code that you're otherwise going to generate for this C function here. Volatile means don't help me, don't optimize this, don't think you know what you're doing, just do as I say. Don't do me any favors, okay? The favors that the compiler can do is completely remove this. It can put it in a different place, reorder these instructions in here to optimize something. I don't want this optimized, okay? Just don't do it. So what does the instruction here say? Notice that this is basically the same thing we saw in the CRT0.s, except for I put %0 in where the register number is supposed to go. So what's that all about? In a C program, I have no idea what the compiler is going to do. Where is that variable? Is it in a register? Is it in memory? I don't know. Where is it? Which register is it going to go in? I have no idea. So what I'm going to negotiate with the compiler here, if I put a %0 in here, in the middle of this instruction, I can tell then this assemble statement here that this %0 is going to be a register, and I'm going to assign it a value with this instruction here. The compiler has no idea what this is supposed to do. I have to tell it. What I'm telling it is this operation has a side effect. It's going to write a value into a register. And I don't care which register it is. Let the compiler choose, but whatever one you use, make sure it holds the value for this variable. So this is how I can say, execute this instruction, store the results in this variable here, and read register number F14, which you can read about in the RISC-V Privileged Instruction Manual in Chapter 2, where it describes how this function here works, and put it in the variable here, which is part of my C program. That then become recognizable by the rest of my code. All right? So this says, give me the heart ID, and then I'm going to set it to 1 in this array of flags up here, okay? As well as return it down here. So let's go ahead and make this program. All right. Now let's do the nm command to see where everything is. Right? Here's my heart flags down here at 2884, because I got to know, where the heck is all that stuff. I can go find it when I'm done running the program. Because it's a C program, it's got all the usual junk in here in case the library needs it, right? Okay. So let's just run it and make sure that everything works. Well, there's a little more going on here this time, but like I said, it's real easy to just go to the termination part down here. It's a very good sign when the two hearts stop as a result of executing an e-break instruction, right? That's a very good sign, okay? Now let's look and see what the state of each of these two hearts is. Heart 0 terminated, program counter sitting there at 64. Heart 1 terminated, and the program's counter sitting there at 80 rather, okay? Does it make sense that these both have different values when they're done? I mean, on the one hand, they both executed main. How come they ended up in a different spot? It's because CRT0 called them from different places and they halt in different places. It makes perfect sense that these would be different, okay? Register X2 in both cases are the stack pointers. We can see those are different, as we would expect, okay? Let's look at register 10, which is right here. Hart number 1 has a 1 in there, and hart number 0 has a 0 in there. These are exactly what they're supposed to be when the main function returns. So far, so good. Now, I forgot where the heck this thing is, right? The hart flags. Let's look at 2884. Run it again. Let's search for 2884. It's probably only in the... Well, there is one of the things writing something into it, right? It makes sense because the C code has to access it. And we'll do a lot of... Let's go to the end of the file and search backwards, okay? So 2884 is right here. And I wasn't thinking, if I want to actually find that in the memory dump, remember each line starts with a 0. So let's search for 2880. And there is the place where the flags are located, right? So here's 2884 in our dump. And remember, it's supposed to be, what, 64 bytes of data, which is this many bytes here. Okay? So we have 2 flags set to a 1, and all the other ones are set to 0. And that was in the BSS, right? So this is probably the end of the BSS that got zeroed out by hart number 0 and so on. Okay? If we go to the bottom of the memory dump, we should be able to see, there you go, you can see something got written into the stack down there. Well, which stack is this? And what is this stuff? It's at 2FF0. Well, remember, hart 0 has its stack starting at the very end of memory, so it would have started at 3000 if we go back up and look at it. The other hart would have started at, what? 2F0. So here's the stack for hart number 1. We'll see nothing ever got written in there. Or it got written in there and it's stored in A5, which is unlikely. So why would this stack have data in it and this stack up here does not? Well, we first check. Let's make sure that we're looking in the right space, okay? Does the stack for hart 0 really do start at 3000 in hex? And the stack that's used for hart number 1, does it really start at 2F00 and work its way down from there, okay? Let's back up here. Plenty of data. Well, yes, they do. All right, let's go back to looking at CRT0.S, okay. Are they both supposed to end in different spots? Yes. Hart 0 should end there. Hart 1 should have ended down there. So that confirms that. Now, what about the stack stuff? They both call main. But remember, hart 0 also called this thing here. I suspect strongly, if we look at what the main does, which is almost nothing if you think about it, it doesn't use any of the stack at all. It doesn't need to. We didn't do anything in there that warrants it to be saved and reloaded. It only probably used the temporary registers. This function up here is probably more complicated and used the stack. That's what's going on there. That's why that happened. If you really want to know for sure, we can look it up in here. Let's see what the compiler did for main. Here's our main. There's the entire main function. Does it use the stack pointer for anything? No. Do you even see an X2 anywhere in here? No. It never wrote anything in, never moved it, didn't do anything. Done. All right? There it is reading. What we see is the hart ID register number. The disassembler here that generates the listing knows what this thing does, and it tells you, oh, by the way, you're reading the hart ID number. Okay? In theory, you could actually put that in your source code too. All right? Because it's an alias for that register number. If we go down here and look at the init C array, remember this is what's called in hart 0. Look what happened. The very first thing it does is it backs down the stack pointer by 16. Then we see it storing stuff into it. So that obviously is what's going on in there. All right. So this all makes perfect sense. We have separate stacks. We fired up 2 threads, 2 harts. We both called main, and main decided that one's going to do one thing and the other one's going to do something else. So let's look at another one. All right. Now, I did not touch the CRT0S here, but I did make an update in the main file. It's going to go on here. So we know that we know this all works. Haven't touched this at all. This is how we can get the heart ID number into a variable here. I can now finally get to the point where I put my switch in there and I say, look, if I'm thread 0, do the stuff for thread 0. If I'm thread 1, do stuff for thread 1. And when I'm done with main, because remember, every one of the hearts is going to execute this at the same time. Again, I'm going to still return the heart ID. So what do those two separate things do? Well, one of the threads, the thread for heart 0, is going to say, hello from thread 0. What's it going to do? It's going to copy what's happening up here. Look at this, align as. What I really have is this two-dimensional array of characters. I want 16, I'm going to use them as strings, C strings. I want 16 C strings, each of which are 128 bytes long. So the first string at T message 0 that can hold up to 128 bytes will be filled in with this text here. This one down here will fill in element number 1 of T message with another string down here saying hello from thread number 1. Right? That's all fine and dandy. What the heck is this thing doing? Well, it's annoying to go find things in a dump that don't start at nice round numbers, as we noticed when I looked for the flags, right? They're kind of in the middle of nowhere and don't start in a nice place. Well, what I can do is say align as. If you include standard align.h, okay? I can say align as if it needs to be on a boundary that's a multiple of a hex 100. Obviously, a character array could just start anywhere because it just has bytes in it. The compiler will put it any old place. But this thing tells the compiler, no, you have to put this thing in memory starting at an address that's a multiple of 100. So let's go ahead and compile that one up. Let's look at the addresses here for a minute. There's T message. Look at its address. Nice. We can find that. It won't be strewn all over the place in the dump. Okay. What else do we know? Here's our init done flag. It coincidentally happens to start at a nice clean address as well. So init done flag, which we know works. We've seen that one before. This is all about the T message at this point. Let's go ahead and do a make run pipeless. If I can spell. Fires up. Let's go to the termination messages. Okay. We fired up and ran 2 threads. Looks like we started with a little bit more memory this time. So the stack for heart 0 is at 4000 in hex. And the stack for heart number 1 is at 3F00 in hex. They both returned their heart ID numbers in register X10. All that makes perfect sense. Now if we go through the dump here, we're going to see 2 things. Look at this. It's strewn all over the place, and this is not where it's supposed to be. These are the literals. Right? If you ever, wrote assembly language on a mainframe, you have to say ltorg every now and then to say, put all the literals here. Well, that's what the compiler does too. In order for me to copy a string into a variable, it has to have one to copy it from. So this is the string that it's copied from. The literal in the string copy function call is stored right here in the middle of the text region. And then we have the BSS and the data region, stuff like that. A bunch of other junk that has to do with, libraries and things like that. Now here we go. Here's the T message. Two-dimensional array starts right there, right? We just saw that when we looked at the addresses. Nice, clean multiple of 100. So obviously this got copied in, followed by a null, right? These other nulls are sitting here because this is in the middle of the BSS. Heart number 0 zeroed all this stuff out before it entered the main, right? So thread number 1, when it copied its string, it started in element number 1 of the two-dimensional array, right? So that all looks pretty darn good. Let's go down here and look at these stacks, right? Here's the stack for heart 0. It's got a little stuff in there, a little bit more than before. Now look what's happening up here. Now heart 1 also used its stack. And that makes perfect sense. Main had to call a subroutine. So at an absolute minimum, in order for the main to execute these calls, main has to at least store its value that's in register X1 so that it can do its return, right? Because when it calls this subroutine, the subroutine here returns back to main by using register X1. So main has to store the registers in order to call these subroutines, okay? That makes perfect sense. Now, before I go, let's look at one more quick example here, all right? What happens? I mean, so, this is all great and fine and dandy, right? But we got a problem here. What would happen if I declared a variable on my stack that's really big? 300 bytes is more than hex 100. Remember, each stack holds hex 100 bytes, which is 256 in decimal. So if I declare an array as a local variable in main, the storage to hold that variable will be on the stack for whatever hart is executing this. So we're going to have a data array in the stack for hart 0, a data array in the stack for hart number 1, and for any number of other harts that might be running as well. And because I made this thing so big, it will, as we say, overflow the stack. And because the stacks are all next to each other, when hart 0 fills this in, it's going to write it all over the stack that belongs to hart number 1. When hart number 1 fills that one in, it's going to write over whatever comes underneath its stack, which would be the heap, right? But, that thread would destroy whatever might be in use down there, okay? So this is the only change I made so far. Let's just see what happens if we do this, right? Make run pipe less. And this is where we're going to see why I had to update my simulator to add the check for the PC alignment problem. So let's search for terminate and see how this thing ends, right? And what we find out is that thread 0 runs and it ran into an e-break somewhere, somehow. And we'll see that actually it terminated okay because its stack wasn't ruined. But hart number 1 had a little trouble over here. Okay, why? Well, as you can see, here's the last instruction that hart number 1 executed. It decided it was going to do a jailer to its X1, and as I just said, remember main had to store the copy of X1 in its stack because it called a subroutine, and it needs to get its old value back again. Well, when it read it back, look what it got. It got 232323. Is that the right address? I don't think so. There's not that much memory in the simulator here. Okay, so it branches to this address here. And because jailer shuts off the least significant bit, if you do the math and look at these two values, this is an odd number. This is a multiple of 2, but it is not a multiple of 4. So this hart halts itself at that point, because this is just not a legal value to put in the program counter. So it stops and it prints out that alignment error. And I showed you that earlier on when I talked about the changes I made to the individual harts, okay? So when this whole thing ends, hart 0 registers look like this, which actually look pretty reasonable. Hart number 1's registers look just broken. First of all, where did that come from, all right? That's kind of messed up. There's another 2323 over here. This just looks suspiciously broken, okay? Now let's go to the very bottom of the dump here and look and see what happened. Remember, the stack for hart number 0 is down here. It starts at, in this case, it would be 4,000 at the end of memory, right? And it works its way down. So hart 0, when it entered main, stored a bunch of registers in here, and then it declared a variable and filled it in. And 300 in hex would have taken it down to about here somewhere, okay? Which writes over where the stack is for thread number 1. Now, when thread number 1 runs, remember, it starts at here and it goes down into the heap. All these 23s, what are they, right? Well, it turns out that the ASCII character code for a pound sign, or the hash, is 23. That's where all those 23s came from, all right? So, in the end, nobody ruined the stack for hart 0, so it ended okay. But hart 0 ruined the stack of hart 1, and it didn't end well at all. Okay? So that's where that all comes from. So what's the takeaway here? Well, you need to know how big your stacks are supposed to be at all times. And when you create them, make sure they're big enough. So down here, what would we do? Let's just comment this thing out. let's shift it left another bit. If we shift it left 9 bits, then what it would be is that would be times 200 in hex. Okay? One more bit of zeros, right? If we make this one, and then we run this, it should exit okay. Let's go to the bottom of the whole thing. You can see now stack for heart 0 is down here. And yes, heart 0 did write all the way up into here, okay? And then some. It wrote all the way up to there, okay? And this was before part of the stack belonging to the other thread, which is now way up here, okay? Instead of being 100 in hex, it starts at the maximum memory minus 200 in hex, which is this. And it works its way down from there. Both of these exit properly, and I think if we go back to the termination messages up here, we'll see it did what we wanted it to, and everything's fine, okay? They both end with an e-break. They both end in different places because they're supposed to, okay? So, quick recap. What have we done? We've figured out how to initialize an address space so that we can run more than one heart at the same time. The key to the whole thing is make sure that each heart has its own stack so that it has its own context when it calls its main functions in here, okay? So they can all act differently. It acts differently based on their heart ID numbers, 0, 1, 2, 3, and so on. We have allowed one heart to do the zeroing of the BSS and the initialization of the C library and so on by using this single init flag in here. And that init flag is used to synchronize all the hearts so that none of them proceed beyond where they're supposed to before the memory has all been initialized to let it do so. Specifically, zeroing the BSS and initializing whatever variables need to be set up in the C library. Thanks for watching. See you next time.